Okay, so we have a cool study here about fungus and some details about edible fungi, mycoforestry, or fungus agriculture, farming fungus for food, or to facilitate the growth of plants that we're also growing for food, or to use the plants to grow the fungus for food. This is really interesting stuff. I love reading about all the various uses for fungi that we find. Perhaps the most wild use that I've read about is the idea of using a UV absorbent, heavily pigmented fungi as like a shield layer over spacecraft or like colony structures or buildings that we build on the moon or Mars. And what's crazy is that if you could sustain that fungus with like a nutrient stock inside the ship or inside the building, that's feasible. You could totally do that. Like you could make a radiation shield with fungus. But here they're talking about agricultural fungus, and this is really interesting, really cool stuff for like food production, as well as forest maintenance. We were just talking about a news article about protecting old growth forests, so this is right in line with that. So let's read the abstract, and then we'll go through this article here and just see what's going on. Demand for agricultural land is a potent accelerating driver of global deforestation, presenting multiple interacting issues at different spatio-temporal scales. Here we show that inoculating the root system of tree planting stock with edible ectomycorrhizal fungi, called abbreviated as EMF, can reduce the food forestry land use conflict, enabling appropriately managed forestry plantations to contribute to protein and calorie production and potentially increasing carbon sequestration. Wow, so that's really cool stuff. All of that is really good. So basically, not to get ahead of myself here, before I'm sure they're going to expand on this in the article, but obviously land use is a contentious thing because if you want to farm or you want to ranch, have a ranch to graze some animals like a pasture, that's going to use a lot of land, and you often need to cut down forests. But forests also have value, both ecological and environmental and economic value. And so there's all these different tensions and influences, pushing and pulling to create this kind of forestry land use conflict, or food forestry land use conflict. But here they're suggesting a potential solution with fungus that could improve the health of the forest, produce food, namely proteins, and increase carbon sequestration. So this is incredible. Like, you gotta love really imaginative solutions like this that have nothing but upsides. This is awesome. Okay, I shouldn't say nothing but upsides because let's get to the next sentence here. Although, when compared to other food groups, we show that EMF cultivation is inefficient in terms of land use with a needed area of 668 square meters per year per kilogram of protein, the additional benefits are vast. Depending on the habitat type and tree age, greenhouse gas emissions may range from negative 858 to 526 kilograms of CO2 kilogram equivalents. I think this. Okay, sorry, I misread this. Minus 858 to 526 kilograms of CO2 to the equivalent kilogram of protein. And the sequestration potential stands in stark contrast to 9 other major food groups. Further, we calculate the missed food production opportunity of not incorporating EMF cultivation into current forestry activities, an approach that could enhance food security for millions of people. Given the additional biodiversity, conservational, and rural socioeconomic potential, we call for action and development to realize the sustainable benefits of EMF cultivation. So this is cool. So perhaps the protein development wasn't as awesome as some other methods or as they were hoping, but the additional benefits are vast, and it seems like it'd be really easy to do. Like, this seems like one of those things, like adding lights, green lights onto fishing nets to discourage like turtles and dolphins from getting caught up in the fishing nets. It's a really easy solution that's economically feasible that you could implement tomorrow. It's like one of those like perfect solutions that's both effective, like chemically, biologically, but it's also economically feasible and practical, and we can do it easily. Like a small business person could do it. Somebody who's just like an amateur cultivator themselves or an amateur fisher could do something like this, like the example I gave. Okay, so let's get into the actual meat of the article. skimming some of this. Some charts, material smells. Okay, we can read this. Many of the world's forests are highly degraded, and despite significant afforestation activities, net loss of forest area remains high at some 4.7 million hectares per year. Demand for agricultural land is the biggest driver of global deforestation, and this is forecast to accelerate. Deforestation presents multiple interacting issues at different spatio-temporal scales. Forests house much of terrestrial biodiversity. They sequester 2 gigatons of carbon per year, and 75% of the world's accessible fresh water arises from their watersheds. At the same time, climate change presents an accelerating risk to food production systems. Increased extreme weather events, trends towards less predictable weather cycles that reduce harvest yields, and climate change-driven desertification all negatively impact agricultural output, risking the need for more land to even maintain existing levels of agricultural production. Pathways to reduce this inherent land use conflict exist. Agroforestry, involving the addition of trees to agricultural landscapes or farming and forest landscapes, is one well-established approach, but such systems do not recreate natural forests, and economics typically favor monocultures with commercial agricultural practices. However, the cultivation of edible ectomycorrhizal fungi, or EMF, in mycoforestry presents a promising emergent technology that combines food production with afforestation while meeting conservation and biodiversity priorities. Okay, so here they describe the fungus a little bit. EMF are plant symbionts, exchanging nutrition for plant-derived carbohydrates through a structure with the host plant's root systems known as mycorrhiza, and they include over 900 edible species. So in other words, the fungus is more effective at extracting water and minerals from the soil, and so it does that. And the plant is photosynthetic; it produces sugars, with exposure to water and sunlight. And so the fungi can share this water and this minerals that it picks up with the tree or the plant. And the plant, in return for this water and minerals, will share some of its sugar with the fungus so it can grow. It's a really beneficial mutualistic relationship that's existed for hundreds of millions of years and is pretty much responsible for the entirety of the vegetative layer over the entire planet. So, kind of important. Since the 1970s, the paragourd truffle, Tuber melanosporum, a climate-sensitive Mediterranean EMF, has been widely and successfully cultivated. Aside from the tuber genus, cultivation of EMF has been an under-researched field, and although progress has been made with the cosmopolitan Suillus and Astreus genera, the greatest advance has been in the widely distributed Lactarius genus, and mostly with the appreciated European Lactarius deliciosus. Experimentation with L. deliciosus presents annual yields of up to 1,089 kilograms per hectare, dependent on the methods employed. Additional experimentation has also been successful in France and in New Zealand, where a markedly higher production figure of 3,000 kilograms per hectare has been reported, although this latter report is lacking in detail. You might have some private production companies inflating their numbers a little bit. Nevertheless, the figure of 1,089 kilograms per hectare gives a good indication as to what is possible, and as the field is expanded, it's expected that more species will be identified with different bioclimatic preferences and yield potentials. Although the field is nascent, it shows great promise, and a full roadmap has recently been published suggesting implementation in the neotropics to combine biodiversity and conservation goals with food production and afforestation using Lactarius indigo. The harvesting of EMF can play an important role in rural socioeconomic development by providing a significant food source. Another potential major benefit is carbon sequestration and the ability to help mitigate anthropogenically driven greenhouse gas emissions and the resulting impact on the climate. Proposed EMF cultivation involves tree planting as orchard-like systems or methods closer to afforestation with conservation goals. But in either method, understanding of the greenhouse gas flux of the plant partner component was previously unknown. Okay. So here, this is a picture of global distribution of 3 Lactarius species with cultivation potential. So the yellow dots are Lactarius deliciosus, the pink dots are Lactarius indigo, And the blue dots over here in China, and a couple in Japan, and one in the Pacific Ocean islands, is Lactaria subindigo. And these are compiled from georeferenced records from the Global Biodiversity Information Facility. And so they're showing annual afforestation rate in millions of hectares. Okay, so just looking at the data, you don't see any obvious trends. Like USA has a lower rate, but they have about an equal mix of pinks and yellows. Canada has a bit of a higher rate, but it looks like they just have yellows. Although perhaps there's pinks in Canada, but they just haven't been sampled, or perhaps they're all just south of the Great Lakes like that. You never know. Sweden looks like it's all yellow, and it's particularly low. So maybe Lactarius deliciosus has lower annual afforestation rates, or it's associated with that. Meanwhile, China has a really high rate, and it has one yellow and a couple blues, but super sparse, not a whole lot of replication going on. So again, difficult to derive any kind of trends just by looking at it. But that's what the results and discussion section are for. So let's get into this. We estimate the potential of EMF cultivation by integrating production figures with current data on greenhouse gas flux of wooded systems. Combining data from 637,000 ground plots and 707,561 waveform light detection and ranging, or LiDAR, observations alongside additional satellite data, each hectare managed as a tree crop in boreal systems may sequester around 12.8 tons of CO2 per year. Whereas in temperate ecosystems, this is likely to be around 6.1 tons of CO2 per year. And in tropical systems, the flux may be very different, with instead an emission rate and instead of a sequester rate of 3.8 tons of CO2 per year. This difference is largely driven by the dataset incorporating carbon emissions in wooded environments such as commodity-driven deforestation, which is globally concentrated within the tropical climate domain. Although accurate for current socioeconomic environments, these figures may be a significant underrepresentation of carbon storage for productive EMF forests. These will likely be coveted by local beneficiaries and therefore less susceptible to deforestation. So it's kind of like what I was talking about with the Tongass in Alaska. The Tongass is an old-growth forest. It's like one of the last ones in North America, or at least in Alaska. And there was recently talk about logging in it, developing a big road to go cut down a bunch of the trees. And like they're saying here, likely coveted by local beneficiaries. Yeah, there was a ton of local protest against logging in the Tongass. And I think, I haven't been following the issue too closely lately, but the last I heard, they were really, I think, backtracking and thinking about just, okay, we're not going to touch the Tongass. Too much hassle. So, I mean, that's cool. You see that elsewhere in the world as well, especially in tropical areas where you have so much more biodiversity. Okay, Compared to our 9 most important food categories, only EMF production can present a net sequestration of greenhouse gases during production. Interesting. Viewed in terms of land use, EMF cultivation is less efficient, presenting a land use of 668 square meters per year to derive a kilogram of protein. This is higher than all food production categories aside from beef production, which includes extensive pastoral systems with an upper figure of 2,100 square meters per year to derive 1 kilogram of protein. However, land use figures should be interpreted in the context of EMF cultivation providing additional ecosystem services, greenhouse gas efficient food production, and at the same time reducing the food forestry land use conflict. In this latter context, we have further explored the potential scale of such an approach. Current per-country afforestation rates, annualized for the period 2010 to 2020, have been published. Combining these with yield data and our nutritional calculations, we present the missed opportunity in terms of food production. Okay, so I'm not going to go through all of this. Using the average suggested daily calorie intake per adult of 2,250 calories, we see that the forestry activities of China for the period 2010 to 2020 could have set in place a production system capable of enough calorific output to support 4.6 million people annually. Globally, with annualized planting rates of 4.7 million hectares, this presents a missed opportunity of enough calorific output to feed up to 18.9 million people annually. Crucially, this may be achieved by only modifying the planting stock in current afforestation activities, and this can be a cost-effective process using spore-based or cultured inoculum. So basically, they're saying that, if I'm interpreting this correctly, they're saying that the most cost-effective way to do this would just to use some fungal cultures inoculated in trees that are being planted in some of these like tree farms, like big areas where forests are grown specifically to be harvested at certain times, and they're next to other plots of forests that are grown at planted at different times so that they can be harvested at different times. Blah blah blah. It's the whole commercial tree growing thing. And if you were to inoculate these trees so that they grew this fungus at their base, you could harvest this fungus regularly as the trees are growing. The fungus would help the trees grow more by providing more nutrients and minerals and sequester more carbon as a result. And then by the time by the time came to harvest these trees, the fungus has boosted their growth enough that you might be able to improve your wood production, and so that means more profit for the loggers and the wood sellers, all that commercial activity. So you can see how just that simple addition of the inoculation of these commercial trees in these tree farms, you can see how just that simple, totally feasible, economically viable process has all of these downstream benefits of carbon sequestration, food production, increased wood production. It's awesome. And it's cheap. And so this is one of those things that you definitely are probably going to see put into practice in real life sooner rather than later. So they say, continuing, aside from a calorie and protein source, EMF are nutritionally valuable in terms of antioxidants and the provision of essential fatty acids. So it's not just protein that they provide, but all sorts of other chemicals as well, like antioxidants and fats. Harvests may be consumed fresh, they may be dried or processed for protein extraction. However, not all tree species or planting scenarios will be suitable, and greenhouse gas flux will be influenced by stand management. So basically it depends on what kind of trees, what kind of fungus, exactly, what climate you're in, what environment you're in, etc. These deficiencies may be balanced by the conservative yield estimates used here, and so the potential to increase afforestation activities at the same time as mitigating the farming-forestry land-use conflict remains high. Moreover, forests and trees and agroforestry systems provide an array of ecosystem services, including water and microclimate regulation, shade and windbreak provision, soil protection, nutrient cycling, biological pest control, and pollination, alongside providing habitat for a diverse range of species that can reduce or reverse local biodiversity loss. So there you go. There's a whole laundry list of more benefits, more downstream, secondary, tertiary, quaternary, ecological benefits. The technology is nascent, and more research is needed. Nevertheless, with such stark global potential, we must urgently pursue such options, and we call for more researchers to join the field. We have highlighted the opportunity and the tools exist to take this forward. We need policymakers and research, funding, and development agencies to help make such options a reality. So, really cool stuff, really exciting. And like I said, to make that a reality, you need it to be not just effective scientifically, chemically, biologically, whatever you want, but it also has to be feasible, logistically feasible, economically feasible, practical to install for the everyman to use, for the small business owner, for the farmer, for the fisherman. It has to be something that they can use at their small scale with their meager budgets. And something like this, these edible fungi crops planted into like commercial tree farms or whatever, to produce food and also boost wood production, plus all of those other downstream ecological consequences, there's enough going on here that I think this is something that we would see developed and put into practice yesterday, if not tomorrow.